we present planning to explore via self-supervised world models. Many approaches to reinforcement learning operate in the paradigm which assumes unlimited access to the environment and rewards. An agent is then trained by iteratively acting in the environment, retrieving the reward, and updating the policy. This requires a carefully engineered reward for training. It is not only tedious, but also makes the agent specific to that particular task. Recent work has pushed for lifting the assumption of availability of the reward, letting the agent explore the environment on its own. However, these approaches are hard to fine-tune to a particular task since they are based on policy networks or Q-learning. Instead, we propose a self-supervised model-based agent that is able to adapt to a new task in a zero-shot manner. Our agent, Plan2Explore, interacts with the environments without reward in order to collect new data. It then uses the data to train the world model. Once the model is updated, the agent seeks to improve the model further by collecting more data. After the model is trained in such self-supervised manner, we can use it to solve a specified task, such as standing, walking, or running in this case. A single self-supervised model can be used to solve all these tasks. To dive deeper into our approach, our world model consists of an encoder that compresses images into latent states, an action-conditioned latent dynamics model that predicts the future latent states, and a decoder that produces the images. We train the model with the evidence lower bound. Using the world model, we can plan to explore by maximizing the novelty of imagined future states. We will want to encourage the agent to visit states about which it is uncertain due to missing knowledge. That is, we want to measure epistemic, but not aleatoric uncertainty. We can measure epistemic uncertainty as the disagreement of an ensemble of latent models. Intuitively, the ensemble initially disagrees on the new data. As the models are trained on the new data for longer, their predictions converge, and the disagreement reduces. We can measure latent disagreement in the latent states imagined by the model and use it as the intrinsic reward. Our agent then plans to explore by searching for a policy that maximizes this intrinsic reward in imagined sequences. The agent is able to plan to reach states that are far from the seen states, while a model-free agent would only explore within the replay buffer. We learn a value function for the intrinsic reward and train the exploration policy using the value function and gradients through the model. Overall, planning to explore is enabled by a powerful world model, using which our agent is able to learn very efficiently. In turn, the agent is able to collect novel data that allow the model to improve, leading to a virtuous cycle between model learning and exploration. Next, we show the resulting self-supervised exploration policy. We evaluate our self-supervised approach on 12 continuous control tasks with the image inputs, where it is consistently able to learn effective exploration policies. Can we now use our self-supervised agent to solve a new task? In this scenario, we are giving a new task that is specified by a reward function. We can learn to solve the new task entirely in the model imagination, without requiring new interaction with the world. We use the same model as trained during exploration and learn a task value function and a policy to produce the task agent. Even though our agent is not allowed to practice the new task, it is able to learn effective policies that solve the task in such zero-shot manner. On hop or hop, our agent in fact outperforms the state-of-the-art agent. And on half cheetah, our agent produces an unorthodox zero-shot policy, which obtains a reward only slightly lower than that of state-of-the-art. Now, we provide our agent a small amount of supervised fine-tuning. With a few supervised episodes, our agent is able to quickly adapt its behavior to the task. On the half cheetah task, it changes its behavior to a more standard one. We provide the agent the reward only near the end of training. As soon as the reward is provided, the agent's performance jumps, here in green, in zero-shot manner, almost to Oracle level, here in orange. With a small amount of supervised data, the agent reaches Oracle performance and sometimes does even better. This observation shows that task-specific exploration might not be necessary to learn effective policies in these high-dimensional continuous control tasks. Our world model is not specific to any task. Can we then use a single model to solve multiple tasks? Here, we show results from a single Plan2Explore model tested on different tasks. We also show a task-specific agent trained on running forward. While it generalizes to some extent to running backward, it fails both flipping forward and backward tasks. In contrast, our agent consistently achieves good performance. We see that our self-supervised agent is naturally suited for multitask RL. In summary, we achieve zero-shot performance comparable to the supervised state-of-the-art with only self-supervised exploration. We match and even beat the supervised agent after adapting for just a few episodes. And our self-supervised model generalizes to different tasks, while supervised agents only learn task-specific models. Please see our code and result videos at this link, and thank you for your attention.